We will extend the notion of independence and redundancy by the notion of a linear relation between vectors. Consider the following definition. Consider vectors v1, v2 until vm, just m vectors in Rn. Yeah, so v1, v2 to vm in Rn. Then an equation of the following type. We write down for a given set of vectors v1 to vm, c1 v1 plus c2 v2, etc. plus cm vm equal to the zero vector. This is called a linear relation between the vectors v1 to vm. So a linear relation exists when we're able to find constant c1, c2 to cm such that the resulting vector in this way is the zero vector. Well, linear relations always exist. Yeah, at least one. Since if we choose c1, c2 until cm equal to 0, so the scalars are all 0, then we obtain what we will call a trivial relation, because of course any component on the sum on the left hand side, c1 v1 equals 0, c2 v2 equals 0, cm vm equals 0. Adding those zeros will typically give the zero vector back. Well, we speak of non-trivial relations if one or some of these c's are non-zero. And what we will show below is that this may happen or this may not happen. So such c's, ci's may exist or not. Well, we have an important theorem, and it's important because we can trace linear dependencies between vectors by applying the following theorem. v1 until vm are linearly dependent if and only if there are non-trivial relations between the vectors v1, v2, vm. So this means that c1 v1 plus c2 v2, if we write down the equation for a given set of vectors v until vm equaling the zero vector, has a non-trivial relation. So there are non-trivial combinations of c1, c2, etc., cm, such that we obtain the zero vector. The proof will be given later. A typical question is the following. So we have a given matrix, a 3 by 4 matrix. A typical question is, are these columns of A linearly dependent? So we show how we may use the theorem which expresses that the columns of A, let's say v1, v2, v3 and v4 as indicated, these vectors are linearly dependent if and only if the equation in c1, c2, c3 and c4 has a non-trivial relation. Which means that not all of the C's must be 0 to get the 0 vector. Now this is in fact equivalent with stating that the matrix vector product, now we put the Ci's in the vector C, then we may express the right hand term as the matrix v1, v2, v3, v4 times the vector C equal 0 has a non-zero solution. So here we have a homogeneous system which should have a non-zero solution. So basically, since these rows of these columns constitute matrix A, it means that this remark is equivalent with stating that AC equaling the 0 vector has a non-zero solution. And of course this happens exactly when we look at the null space or the kernel of the matrix A. Then this kernel should not be equal to only the 0 vector. Well, look at the matrix A here. We have AC is 0, this is a homogeneous type of system of linear equations, so it's consistent. And also notice that the rank of A is at most 3. So if we look at the pivots by looking at the reduced row echelon form, then we get at most 3 pivots, which means that in a homogeneous system there is at least one free variable. Yeah, since we have more columns than we have pivots. This means in particular that we have infinitely many solutions. So there are infinitely many C's which accomplish A times C equal the 0 vector. So amongst them there must be also non-zero ones. Which is actually just what we needed to show. So the columns of A are indeed linearly dependent. So we look again at the same example with the matrix, and we already concluded that the columns of A are linear dependent. So now we try to find all linear relations through the kernel of A. We've seen that actually all linear relations are given by the kernel of A. So what we do now is we calculate the reduced row echelon form, use Gauss-Jordan elimination steps, and reduce the matrix in this way. I think now you must be able to follow the steps that we are using here. Now we clean up the third column and then we're done. Yeah, so we see we get one free variable. The rank of A equals to 3, and the free variable is the 4th. So C4, we can pick C4 arbitrary. So now let's write C4 equal to T for some constant T. So we actually make a choice for C4. Then we may express C, all linear relations, C giving rise to all linear relations such that A times C equals the 0 vector is now minus 5t minus 4t minus of plus 3t and t. So these all multiples, so all linear relations are given by all multiples of the vector -5, -4, 3, and 1. So the kernel is actually the span of the vector -5, -4, 3, 1.